Okay, so 11.1 is inference about two proportions. Okay? So, here's your rules. We've got a few more rules. Number one, it still needs to be simple random sample, and these samples need to be independent. Number two, N1, P1, Q1 must be greater than or equal to 10, and N2, P2, Q2 must be greater than or equal to 10. Okay, we've got two samples now instead of one. Number three, they should be normally distributed with no outliers. And number four, your N1 has to be greater than or equal to 30, and your N2 has to be greater than or equal to 30. And also, your N1 can be no more than 5% of your population of N1, and your N2 must be less than or equal to 5% of the population of N2. Okay? All right. So, I think the easiest thing to do actually is simply do a problem. Okay? All right. 2103 patients in treatment group. 547 get FedEx. 1671 patients in the control group. 368 get FedEx. Is there significant evidence that drug groups have more headaches? Use alpha equal to 0.05. Okay? So, the first question, remember we're going to follow our 8 steps again. First question I'm going to ask you, is this categorical, quantitative, or regression? One of these days it's going to be regression. Okay? Why is it categorical? Because there's a lot of numbers, aren't there? Why is it categorical? Because you either have a headache or you did not have a headache. Those are your categories. Okay? All right. So, the next two questions, not necessarily in order, are what is the test statistic and what is the null and the alternative hypothesis? Which one would you like to do first? Let's do the null. Yeah. Okay, I'll switch it. Okay, so your null and your alternative hypothesis. Okay, so just as a reminder, what does null hypothesis mean?
Status quo.
You said equal, what did you say?
Status quo.
Status quo. I would say, status quo is correct, that's not the terms I've used. No change, no difference, or it's a fair coin, right? So in the context of this problem, what does no change or no difference mean? What'd you say? Okay, so the control equals the treatment, okay? Now we have to convert that to a mathematical statement. So what would be the mathematical statement that would mean no change, no difference? Fair coin doesn't really apply. What'd you say?
Like no change.
Okay, so we've got two different populations here. We've got a drug group, we've got a treatment group, right? Okay? So if there's no change or no difference, they're probably equal to each other, right? P1 equals P2. Now in the past, we've always said it equal to a number. Do you know what the population is for headaches? No idea, right? So we're actually, instead of comparing this to a population, we're comparing them, two samples to each other, directly to each other. Now, if you wanted to, instead of putting P1, P2, that's not very explanatory, you could say P drug equals P control, or placebo, or whatever, okay? That's probably a little bit more sense, makes more sense, okay? Now, what is the alternative hypothesis? Is it not equal to, or what are they asking? Yeah, so we could say P1 is greater than P2, or more appropriately, P of the drug is greater than P of the control. Could I say P of the control is less than P of the drug?
Yes.
I could. Okay, does it matter which way you do it? No. We'll do it the first way just because that's the way we did it originally, but it does not matter, okay? As long as you define those well, okay? All right, so now that we've done our null and alternative, we need to talk about the test statistic, okay? Given this is categorical proportion data, what should the test statistic be? And by the way, my sample sizes are huge, right?
Yeah.
So I should be checking that they're huge, so I'm not gonna worry about it, right? So what should it be? It's gonna be a Z test, right? It's gonna be a Z test, okay? Now, this is a two sample proportion, so it's gonna be a Z test two sample proportion. Okay? Haven't given you that formula. You don't have enough Z formulas yet. I'm going to give you another one. Okay? So here's the formula of the day. Z equals P1 hat minus P2 hat over, square root of P hat times 1 minus P hat times the square root of 1 over N1 plus 1 over N2. Okay, where P hat equals x1 plus x2 over n1 plus n2, this is what's known as the pooled estimate. Okay? So yes, it is a Z equation. This is a new equation. I haven't taught you yet. Okay? Now, I'm going to point out something. The equation I wrote to you on the board is slightly different than the one you're going to get on your formula sheet. On your formula sheet, they have minus P1 minus P2. Okay, let's think about that for just a minute. According to the null hypothesis, okay, oh, we didn't write down our null hypothesis. I'll write it here. What's the null hypothesis again? P1 equals P2. What's the alternative? P1 is greater than P2. Okay, so under the null hypothesis, which we assume this to be true, okay, if P1 equals P2 and I subtract them, what result am I going to get? It's going to be a big fat 0. Okay? So that's why I didn't put it in there. Why did they put it in there? To confuse you. Did it work? Okay? It's always going to be the case. Okay? Under the null hypothesis, we assume they're equal. That's always going to drop out. You need to remember, because this part of it is on your formula sheet. You need to remember that that's going to be 0. Okay? All right. So that's why I didn't put it originally, because I don't really need it. Why is it there? If you're a really math theoretical nerd, it needs to be there, but I'm not. A lot of you aren't, okay? All right, so let's do this. Gosh, we're out of time already. P1 hat, P2 hat, N1, N2, P hat. Anything else I need? Okay. P1 hat, what is P1 hat in this case? 547 divided by 2103. Okay, that's the drug group. P2 hat is 368 divided by 1671. Okay, now we haven't done a lot of math, but let me just ask you really quickly, does it appear that the drug group had more headaches than the treatment group?
Yes.
Yes, it does appear that way. Okay? My N1 is going to be 2103, my N2 is going to be 1671. What's my P hat? And my P hat, I'm going to add up all the headaches. I had 547 plus 368. I'm going to divide that by 2103 plus 1671. Okay? That's what we refer to as the pooled estimate. Okay? So my z-test, two-sample proportion, is going to be my numerator, P1 hat minus P2 hat, minus 0, right? Okay? My denominator, I'm going to do the square root of my pool estimate, this number, times 1 minus that number. That's it. Oh, I forget. Yeah, no, I square root it. Okay? I'm going to do it this way, equals the square root of 1 divided by n1 plus 1 divided by n2. Okay? This is going to give me the numerator divided by the denominator, which is this number times that number. Okay? That's going to give me my z-score of 2.8399, whatever. Okay? So what I've done is I've converted this to a standard normal curve with a mean of 0, a difference of 0. We're saying that the zeroth difference under the null hypothesis. I am 2.83 standard deviations away, right? I want the right side. Doing a right-sided test. Okay? So I need to figure out my p-value equals what? 1 minus norm s disc of that, which gives me a p-value. I'm going to compare my p-value with my alpha, and that means what? Reject, null, and my conclusion is what's my conclusion? There is significant evidence that
the drug group has
more evidence. Okay, I don't want you to say reject if you're not rejecting your conclusion. It just confuses people. Okay? All right. There's a lot of stuff I did not cover. We'll cover that tomorrow. Okay? I did there will be a quiz. It's only going to be on independent stuff. Dependent stuff is in a table. If you see a table, don't worry about it. I didn't cover confidence intervals. We'll do that tomorrow. Didn't cover sample sizes. We'll do that tomorrow. There's a lot of stuff I did not cover. We're only doing this. Okay?
Will you post that on?
Yeah. Okay. Portion test in your notes. Now, I know a while back, we haven't talked about confidence intervals for a while. A while back, I told you that confidence intervals and Hypothesis tests are two different ways to do the same thing.
Oh.
Okay? So what I'd like to do is I'd like to do this exact same problem with a confidence interval.
Did you post this on campus?
Yeah. Is it not there?
Yeah, it is.
Is it there? It is there? Yeah. It's under the notes, not the class worksheets. No, it's under notes. Okay? So confidence intervals. Should be down at the bottom. Okay? So with the confidence interval, what I've got is I've got a new formula for you. And the formula is P1 hat minus P2 hat plus or minus your z sub alpha over 2 times the square root of P1 hat Q1 hat over N1 plus P2 hat Q2 hat over N2. Okay? So you can think of this, remember, it's been a while since we talked about those. You can think of this as your margin of error, which you are adding and subtracting, and you can think of this as your point estimate. Okay? Now, under the null hypothesis, and I know this isn't a hypothesis test, but we said that P1 equals P2, and the alternative says P1, well, it doesn't matter what, well, the one thing I will mention here, in our case, we said it was greater than. Confidence interval is going to be always a two-tailed test. P1 is not equal to P2, because you got alpha in both ends, okay? So you can think of it as exactly the same way. So what we can do here, if my alpha is 0.05, what should be my level of confidence? What's the most common one that I tell you to pick if I didn't tell you? 95%. Okay? So in this case, you can think of this as your point estimate and your margin of error. Okay? Okay, so with your point estimate, it's going to be P1 hat minus your P2 hat. Okay? And then if I'm doing a 95% confidence interval, all I need to do is I go back to here. I'm looking at my confidence intervals for 95% confidence. I get a critical value of 1.96. Okay? So in this case, I'm going to do equals 1.96 plus, no, well, I can't do plus or minus, times the square root of, in this case, P1 hat, which is this number here, times 1 minus P1 hat, divided by N1, which happens to be 2103, plus P2 hat times 1 minus P2 hat, divided by N2, which is 1671. Okay? All right, so you're going to have a lower, you're going to have an upper. Okay? So that's going to be your point estimate minus your margin of error and your point estimate plus your margin of error. Okay? So typically, just as a reminder, when we're doing this, we always write the low number and then the high number. Okay? All right. So, Catherine, I knew wanted some practice in doing confidence statements. So, can you give me a 95% confidence statement?
Yeah, so what would be your 95% confidence is that, I don't know, but it's between 0.01 and 256.
The mean difference is between 0.0125 and 0.0671. Okay, now you can write the confidence statement that way. However, let me just point out here my conclusion of my hypothesis test here. There is significant evidence that the drug group had more headaches. Okay? Now I told you that these are two different methods for doing essentially the same thing. And personally, I like this conclusion a lot better. Okay? So, these actually agree. We can conclude, based on this confidence interval here, I'm going to do that so you can kind of read it. Based on this confidence interval here, we can conclude that there's significant evidence that the drug group had more headaches. Why is that the case? This is where we kind of tie the two things kind of together. There it is. So let's go back to this for a second. Under the null hypothesis, we said there was no difference, right? So if I were to draw my normal curve, we would have said that the difference would be equal to what? It would be equal to 0. There's no difference between those two groups, right? In my case, okay, I found a confidence interval, and I found out that the mean difference was actually about 4%, 0.039, right? Right here, this is the mean difference, 0.03988. Okay, so with my sample, I've got a mean difference of about 4%. Okay, now using the 68, 95, 99 rule, remember we haven't talked about that for life, but just really quickly and easily, what I've said is, well, you know what, if I go out 2 standard deviations, I've got 95% of the area between, in this case, 0.0125, 0125 and 0.0, what was it? 671. 672. Okay? I am 95% confident that the mean difference is between 1.2% and 6.7%. Okay? Is 0 in my confidence interval? No. Okay? So I can safely conclude, because 0 is not in my confidence interval, I can conclude that yes, in fact, there's significant evidence that the drug group had more headaches. Does that make sense? Now, let me ask you a question. I'm going to change this here, just for fun. I'm going to put a -1 here. Okay, so pretend that when I did my math, this is the result that I got. No, I'm supposed to put parentheses there. Okay, this is the result. Pretend this is the result that I got. Is 0 in my confidence interval? Okay, yes it is. I got a negative, I got a positive. In this case, would you say there was a significant difference? No, because 0 is in my confidence interval. Okay? Now, what if instead of, so with my alternative hypothesis, I said that the drug was greater than the control. What if I had said the control was less than the drug? Okay? All of my things would have been opposite, right? So I'm going to put a -1 times this as well. Okay? Now, so if I had flipped this around, the control is less than the drug, all of this would have been backwards, everything would have been negatives, etc. I might have gotten this for an interval. In this case, if this is my answer, is there a significant difference? Yes, there is, okay? So the main thing you're looking for when you're doing a confidence interval for differences, you want those to be the same sign. If they're both negative, or if they're both positive, is it significant? Is there a significant difference? Yes. Doesn't matter in this case. So, if the signs are different, is there a significant difference? No, there's no significant difference. Does that make sense?
Why, hey, the numbers are bigger, they're farther apart when they're different signs.
Okay, so if it's negative, okay, if I got a negative 0.0125, okay, this is my 95% confidence interval. 0 is now within my 95% confidence interval. I've got a negative here, I've got a positive here. So 0 is now within my interval, so there would not be a significant difference.
And why 0?
Because under my null hypothesis, I said there's no difference. So if 0 is in my interval, my null hypothesis is correct. There's not a significant difference.
So he's trying to see zeros outside of your interval.
So you're trying to see, is 0 inside my interval or outside my interval? If it's in my interval, it's not significant. If it's outside my interval, it is significant. Okay?
So if 0 is within your interval, then it is significant.
Not significant.
Not
Okay? So you're mainly concerned about your signs here. Now you can write this statement, and I know this is kind of the statement that, and if you're only doing a one sample test, yeah, this is what I want you to say. But if you're comparing two proportions, really this is what I'm looking for. Okay? Does that make sense? Gonna have to stew on that one a little while. You guys aren't seeming to like this one as much as my last class. Okay, should we move on to something else?
Show the margin of error.
Margin of error is just this piece of the formula. It's your critical value times your standard deviation divided by n. Okay? It's just a little bit more complicated for me. Okay? All right. So let's talk a little bit more. Okay, so in this case, what we've been talking about up to now, these are what we refer to as independent. Okay? So let's talk a little bit about dependent samples. Okay? So samples are often paired, or it could be the same individual measured twice, which is still paired. Okay? And the example I gave at the beginning of the class was you're trying to decide which sunburn works better. So you put lotion A on the right arm, lotion B on your left arm, lay out in the sun, see if you get a burn. Okay? So you can compare them against each other. Okay? Now, my last class, somebody said, well, is that a better way to do it? Well, maybe. So with lotion, you can do that. You can put one on your left arm, one on your right arm, you can compare. If you're doing a drug sample, would it be a good idea to give, say, the baby, the drug, and the placebo? Bound to get better, right? Okay, so it wouldn't be a good idea in that case because you wouldn't know, well, which one helped. Was it the placebo or was it the drug? Okay, so in a whole body thing, you're going to have to use independent samples. But you know, if you're comparing poison ivy treatments or sunburn or something like that, acne, you know, you could put on one side of your face and the other. So that would make more sense. So it kind of depends on what you're doing as to what's better. Okay. And in fact, I guess I would say, if you were comparing, let's say, an acne medication, one of the nice things is, if you put medicine A on one side and medicine B on the other, you can rule out genetics as an issue. Whereas if you compared me versus, say, Marissa or somebody, you wouldn't know. You wouldn't know that as well. Okay? So yeah, it depends on the situation which one you like better. So typically with your dependent samples, they are in a table. Okay? And your table is going to be set up something like this. You're going to have some sort of a treatment. Treatment A, you're going to have a treatment B, okay? 2x2 table, something like this. You're going to have success or failure, and success or failure. Okay? Now, the way that we've labeled this, and I don't know why they picked the letter F, but they did. F11, row 1, column 1, F12, row 1, column 2, F21, F22. So that's the way that the table is. Okay? So your null and your alternative hypothesis, just like with the independent samples, are going to be just like this. Okay? And in fact, the one thing that I will mention, when it's set up like this, P1 equals P2, your alternative is pretty much almost always going to be P1 does not equal P2. It's almost always going to be two-sided. Because you can't really tell which one was better for the way the table's set up. Okay? So it's almost always two-sided in the dependent case. With the independent case, it could be less than or greater than. Okay, as well. In this case, the one thing that you need to remember, the rules, okay, are that F12 plus F21 must be greater than or equal to 10. Otherwise, this isn't going to work very well. Okay? So let's do an example. Okay? All right. So you want to treat poison ivy rash with 2 ointments on the same person to see which works better. Okay? Alright, so if you're doing it on the same person, it's got to be a dependent sample, right? So the dead giveaway is ointment A, you got ointment B, you're going to have success, and maybe I'll write it this way, healed or not healed, and healed or not healed. Okay, I'll put these in boxes so it's a little easier to see. Okay, so you got 293 that were healed with either ointment, the word great. You have 43 where it was healed on B, but not on A. You've got 31 where it was healed on A, but not on B. And you got 103 that didn't heal either one of them. Okay? So the formula in this case is going to be Z equals the absolute value of F12 minus F21 minus 1 over the square root of F12 plus F21. And that's going to be your formula. Okay? So really, in reality, what we're trying to do is we're trying to see where it failed on one but healed on those are your most two important things. Okay? That's what we're really comparing. Okay? All right, so in this case, okay, your null hypothesis is P1 equals P2. The alternative hypothesis is P1 does not equal P2. Okay, this is always going to be a two-sided test. Okay? Alright, so you're going to get your z-score. Okay? Now, notice this has an absolute value here, which means it's always going to be positive, right? Okay? So if I want the absolute value of this minus that, minus 1. Okay? That's your numerator. Your denominator is going to be the square roots of this plus that. Okay? I'm going to divide those two numbers. That's going to give me my z-score. Now the one thing I just want to mention again, because I'm using an absolute value, that's always going to be positive 1.27. I'm going to want this area here. I'm also going to want this area to the left of negative 1.27. Okay? Alright, so when I'm finding my p-value, I want equals 1 minus norm S of that. Right? And then I want to double it, because it's a two-sided test. So in reality, this is really the true p-value here. Okay? So based on that, I'm going to compare my alpha, which did I get? Yeah, I didn't, so what are we assuming? 105. So I reject or do not reject? Do not reject null, which means there is what? Not significant, or maybe I should say no difference between appointment A and B. Or maybe I shouldn't say no difference. There's not a significant difference. I'll put that. Not a significant difference. Appointment A and appointment B. Yes?
So instead of doubling your p-value, can you just divide your alpha by 2 and then compare? Would that be the same?
I'm trying not to confuse people, so I'm going to pretend I didn't do that.
Okay, I'll pretend I didn't say it.
But technically, that's okay. I want to keep everybody on the same method. Otherwise, I'll confuse them. Okay? All right, so the one last thing I didn't cover, sample size, okay? It's just a formula. Just look it up, okay? Now, just as a reminder, plug it in. You've done sample sizes before. The one thing I will say, if you've got, let's say you get an N of 25.2, what does that round to? 26. Rounds to 26. Always round up, okay? And that 26 means I need 26 in group 1, I need 26 in group 2, for a total of 52. Okay? So the N is per group, not your total sample. Okay? So you need 26 in group 1, 26 in group 2. Does that make sense? It's a pretty easy formula. I think you guys can do it. Quiz tomorrow is the rest of 11.2. You see that one? Okay.
You mean the rest of 11.1?
So the rest, sorry, 11.1, you're right. Yeah, rest of 11.1.
So this whole lecture is 11.1,
Well, we started it yesterday, but yeah.
right? Oh, okay.
So it's not
It said
always
11.2.
Oh, I wrote 11.2, it's really 11.1. Sorry. 11.1. 11.1.